All right, so what do we have? We have our acceleration vector. We want our acceleration vector to be some alpha times unit tangent plus beta times the unit normal vectors. And then we found alpha to equal to v of t, or the derivative, right? And then beta is equal to the curvature kappa times v squared. Okay? So I didn't draw a picture because I couldn't draw a picture. But if we take a look at a curve, now the curve can be in 2 dimensions or 3 dimensions. So let's start by looking at a curve in 2D. Let's take a look at a specific point on the curve. So let's say you're on this point. And let's just say you're getting pulled with an acceleration somehow. Let's say your acceleration vector is going this way. Okay? So what you have is, along your curve, you have a unit tangent normal. No, I'm sorry, unit tangent vector. And then we know that the normal vector is going to be perpendicular to that. And what we want to do is we want to express A as a linear combination of the t vector and the n vector. And the way we do that is we scalar multiply the t and the n, and then we would add them together, and then we would come up with the A vector. So we know that they're unit length, so we know that this distance over here, if you were to project A onto the tangent vector, that's going to be of length alpha, which is equal to the speed. No, not the speed, but the derivative of the speed. And then this length over here is going to be the curvature times the speed squared. So let's do an example. I wanted to do one in 3 dimensions to try to make a point, but I didn't see a quick problem. And you guys only have one in your homework. I feel like if I do it, then that means you don't get to think about it as much. So I'm going to see if I can find one. How am I going to find one? Let's go to the book. So 37 through 42. You guys want to pick a number from there? $39 looks like it's in red. I wonder what that means. Means. Oh. All right, so now that we have a bunch of canned formulas, it's kind of nice for us. Actually, we have to find the curvature. I think, if I remember correctly, that wasn't very nice. Let's, I'm sorry, we need to probably go back and fix this up a little bit. Because here we have to find the speed, and then we need to take the derivative of that. So the question is there an easier way to deal with that? Well, what if I just tell you what they have in the book? So, whenever we do these problems, we're going to be working with the position vector r, right? So if we can get all these in terms of just the r vector, whether we're taking the derivative and magnitudes or dotting them, then I think it'll turn out to be a little bit easier. So alpha, without proving it, is actually equal to r prime of t dotted with r double prime of t divided by the magnitude of r prime of t. And then beta. So now, if we look at alpha, I mean, v prime looked really simple, right? Except when we actually try doing the problems, it might get a little complicated. But now we have everything in terms of r primes and r double primes and magnitudes. So I think it'll be easier, an easier formula to remember. And then beta, on the other hand, it's going to be a semi-complicated cross product, but I hope we're getting used to that. We have an r prime of t cross with r double prime of t. So I think there's remnants of the curvature here, right? Divided by the magnitude of r prime of t. So this will help us be able to get those formulas or those solutions a little bit quicker, I think, instead of relying on the nice compact equations that they have. So we'll use this. All right, we have our position vector. It's a cosine t, sine t, and t, so it looks like a helix. And we want to know the acceleration vector in terms of the n and the t vector, the tangent and normal vectors. All right, so let's find those. We need to let's get things set up. We need the first derivative, the second derivative, and some magnitudes and a cross product and a dot product. So let's do that. So the derivative is a negative sine t comma cosine t, comma 1, and then the second derivative is equal to negative cosine t, negative sine t, and 0. So that 0 looks nice. We need the magnitude of r prime. So that's a square root of a sine squared plus a cosine squared plus 1. So that's going to give us a square root of 2. So that's not too bad. And then we need the dot product. R prime of t dotted with r double prime of t. So this is going to give us a scalar. And we just multiply. So we have a negative and negative is a positive, sine t, cosine t, plus we have a negative and a positive, so that's a negative, cosine t, sine t. Looks like those two will cancel. And then we multiply this, we get 0. Ooh, 0. So in this case, it looks like there's going to be a 0 for alpha. So there is no tangential component, tangential component. This is the alpha. This is the one that gets multiplied with a t, right, the unit tangent. And so we got 0 for this case. So it looks like whatever this is going to be going in the direction of the normal vector. All right, now we'll cross them. Yeah. Oh, because we have sine t, cosine t. Yeah. Well, it's equal to 0 because of the algebra. And then when we look at the picture, we'll see a little bit clearer why. It doesn't always equal to 0. I mean, the helix is a very nice special curve. And we talked a little bit about properties, and we'll talk about those properties again, and we'll see why it's equal to 0. All right, the next one is a cross product, r of t cross with r double prime of t. Now, I already have those vectors written on top of each other, so I'll just do my cross product from there. So cross out the first column. I have 0 cosine t times 0 minus negative sine t times 1. That's the first component. The middle component is going to be, I'm going to put a negative here, and then I'll see as a negative as a 0 minus negative cosine t. So negative, negative, negatives turns out to be a negative after all that. This is a negative, not a t. And then the other term, the last term, is going to be a positive sine squared t minus negative cosine squared t. And so that's going to give us a constant 1. So let's see if we can gather all this and simplify it. We got positive sine t minus cosine t and 1. But we also want to take the magnitude of that, right? According to the beta formula. We want a magnitude of this, so let's go ahead and take the magnitude of that. So it turns out to be just the same thing, sine squared t plus cosine squared t plus 1. So sine and cosine will give you 1, and then plus 1 will give you 2, so it looks like it's going to be the square root of 2. Seems like a ripoff. So it looks like your acceleration vector is equal to 0 times the scalar 0 times the unit tangent vector plus 1 times the unit normal vector. So it looks like the acceleration is exactly the unit normal. Matt? This? Oh, I'm sorry. This is a plus. It turned out to be 2 negative, so the pluses and t's tend to look. I like to curl my t's, so it makes it different from a plus. But how about if we do that? And then it looks negative, negative. Okay. So let's see the quick visual of this. We have our helix. Now, if you look at it from straight down, it's just like a circle, right? And if you have a circle with just the sine and the cosine without any excess on the speed, like if you had the omega, the frequency thing, make it go faster or slower. It just turns out to be the acceleration just turns out to be pointing inward, right? By the way, we should have computed that. Turns out that this is your acceleration. Which is, if you look at it, it's the same, it has magnitude of 1, so we know it's a unit vector. And if you look at the original function, it's going in the exact opposite of the position. So you're pointing to the point on the helix, and your acceleration is pointing inward. So your acceleration vector is actually going inward. So this is a view from the top, and a view from the side would be, depending on where you are, it would be pointing inward back to the axis. Now there's no z component in your acceleration. There's no z component, so it doesn't go up or down in the z. It just kind of points inward. And by coincidence for this special curve, it turns out that that's exactly what the normal vector is. It's perpendicular to the tangent vector, so it's going inward. Okay? So most of the other curves that you would be dealing with, you would actually have a value for the alpha and the beta. Okay? But for this particular example, it just turned out to be 0 and 1. Questions? Matt? Which one?
Like the alpha and beta.
Oh, yeah. We kind of derived it in the other computer when we were typing. Actually, we derived it up to a certain point, and then I didn't tell you how we got to here, but you can eventually get to these special functions. So I didn't make that connection here. I just did some magic and say, please believe me, and this is an easier formula to deal with than having to find curvature and all that stuff. Okay?
Sounds good. Seems like it would be a lot simpler to do that.
Yeah, because here you have to find the curvature, and here you have to find the magnitude of the velocity, that's r prime, magnitude, and then you have to take the derivative of that. So that's what makes it a little bit more complicated. I mean, it looks simple, right, because it's just v prime. But what is v prime? V prime is the magnitude of r prime. Or v prime is the derivative of the magnitude of r prime. Now that's like 2 layers of steps that we have to take. And the magnitude has a square root, so that could be, you know, who knows what could happen there. Any other questions? All right, so these would be good formulas to have. By the way, in the book, they call this I call it alpha and beta because I just consider them constants, but they call it something else. This is called A sub t, the tangential component for the acceleration, and then they call this A sub n, that's the normal component of the acceleration. So when you're making connections between what we're talking about here and the textbook, they call it A sub t and A sub n. These are scalars. Now, scalars with a t, it could be a function, right? But that nevertheless they're scalars, which means there's no I, j, k components. Okay? All right, good. Well, good luck with that.
So would that be like, would that be a question on the test, or would you want to put that since we already have, or is that a good example of a question?
I think a good example of a question would be more like your homework, where it's actually two-dimensional and it's polynomials instead of trig functions. So two-dimensional means it's a little bit easier. Polynomials means it's kind of easy, except if it's more than to the second power, then some of these computations might get a little bit slightly more difficult, but I think it's manageable. Any other questions? All right. So the outline for your exam will look something like this. You will have 6 problems. And the first problem will deal with parameterized curves and polar coordinates and doing some calculus with it. Slope, area, arc length. I don't know what else we did in that section, but this is stuff from chapter 10. Number 2 will be vectors. You know, I've kind of delivered a couple ways to ask vector-type questions. You guys had a quiz on vectors, and you guys had something else with vectors. Oh, the review sheet. Did you guys get a review sheet? It was online somewhere, right? Was there a solution up there? No? Okay. Maybe we'll do it in class. So, just basic operations of vectors from add, subtract. There's no divide, so there's multiplication. And there's multiplication several levels. There's scalar multiplication. There's dot and cross. And some basic applications where you might have to find angles. You might have to find vectors perpendicular to other things. You might have to find, I don't know, stuff like that. Volumes, the area of the parallelogram or parallelepiped, volume of parallelepiped. So those are like the application type things. The next one are proofs. Well,
You want that, you said on Thursday, review number 6 of the review?
oh yeah, I already collected it. So proof, prove a vector property or something. Property from cross product or dot product or magnitudes or something like that. The next one are lines and planes. Find equations of lines and planes. You have to know all the different ways to write an equation of a line and the different ways to come up with an equation of a plane. Be good if you know how to find the intersection of two planes or two lines. Oh, and the distance between a point in a plane, a point in a line. So that's lines and planes. We spent a lot of time. We spent ended up looking at our schedule. I had it planned for 2 lectures. We ended up spending about 2.5 or 3 lectures on it. Next is a projectile problem. So something that's either 2-dimensional or 3-dimensional. It'll come in layers. You know, usually these things start off with an acceleration, then you find the velocity and the position and answer some questions about it, like the range or distance or height or speed, whatever else might come up. And then true-false questions. All over. So everything that we've talked about, there's true-false questions that can accompany Chapter 10, Chapter 13, Chapter 12. Oh, this is 12. So that's the general layout. Tomorrow we can take a look at the review sheet and start to tackle some of those problems and maybe even go over this home run problem, whether the ball went over the fence or not. Okay, so that's our plan for tomorrow. If you have any questions, bring the questions so that we can talk about it, and then your exam will be on Wednesday.